Okay, now let's talk about section 3.3. Continuity. Okay, so last time we already discussed the limit. There's several different limits. Okay, so but basically we're talking about the basic limit is this one. So the limit x approaching a, fx is equal to L. It just means for any epsilon greater than 0, there exists a delta greater than 0 such that whenever x minus a is less than delta, not necessarily equal to 0, we have ops value fx minus L less than epsilon, right? So in word, it means fx can be arbitrarily close to L if x is sufficiently close to a. Okay, fx is arbitrarily close to L if x is sufficiently close to a, but not necessarily equal to a. Okay, so this is the limits. And the continuity just means here we exclude a, but continuity says we have to consider a. We have this a function is called continuous at a if first a is in the domain of f, and second the limit fx x approaching a is equal to fa. So the limit can be evaluated by direct substitution. Alright, so this is the continuity at one point. Of course, if this a in the domain, it could be the endpoints. If it is endpoint, you're going to replace this limit by the corresponding either right limit or left limit. Okay. So this writing, it means a is an interior point, but it's not necessary interior point. All right. So that's the stuff. And then let's write it in the epsilon delta language. We were going to rewrite it. So it's definition 3.19. So let E be a non-empty subset of R, and f from E to R a function, and then f is set to be continuous at a at a point a in E if and only if given epsilon greater than 0 there is a delta greater than 0. Okay, so here the author tried to emphasize, which in general depends on epsilon, of course, f, of course, and a. Okay, so clearly this delta will depend on f. For different function, you will expect a different delta. And also this delta should depend on epsilon, because we say arbitrary sufficient. Sufficient is corresponding to arbitrary. So these two will be always the factor. This one, A, if it does not depend on A, we will have so-called the uniformly continuous, the uniform continuity, right? Sometimes the function is nice, then this delta only depends on epsilon and f, does not depend on A. That is a uniform continuity, but that's different, okay? So far let's talk about continuity. So depend on epsilon, f, and A, such that x minus A less than delta, and x in E, x is in the domain, imply ops value fx minus fa less than epsilon. Okay, so that's the epsilon delta definition for the continuity at a point. Second, f is said to be continuous on E, on the whole domain, if and only if f is continuous at every x in in E. Okay, so this is the continuity at the point, or continuity over an interval, over the domain. Okay, so the remark 3.20 is exactly what we just here. The remark is that for the continuous function at a point, we have direct substitution as the evaluation of a limit. Okay, f is continuous at A if and only if when you do the evaluation of the limit, you can try direct substitution. Okay, so let me write it here. If f is continuous at A, what we know is actually the following. The limit x approaches A, f x. You see, in this computation, in this evaluation, you actually have two operations. One is a function, the other one is a limit. Continuity says you can exchange the order. You can put f outside, limit inside. And we know that the limit of x approaches A is A. Okay, this evaluation is equal to A. So the continuity is equivalent to the commutativity of f and the limit. If you can commute with f and the limit, f can commute with the limit, then it is continuous. If f cannot commute with the limit, it's not continuous. Okay, so you exchange the order. You can exchange the order. All right, so that's the meaning of continuity. Next, let's see some properties or the characterizations. Suppose that E is a non-empty subset of R. A is inside E. and f is from E to R. Then the following statements are equivalent. Okay, the following statement equivalent. What is the statement? 1, f is continuous. At A in E. 2, if xn converges to A and xn in E, then fxn converges to fa as n approaches infinity. Okay, so here this is the definition the epsilon delta. This one is actually the sequential characterization of the continuity. Whenever you have a convergent sequence to A, then the corresponding value will converge to fa. Then function f is continuous. Okay, so I have something in my mind. So here the following statement are equivalent. Sometimes they write this one. The following statement are equivalent. Okay, the following are equivalent. If you don't write statement, the following are equivalent. TFAE. Sometimes. Fancy notation is not important, but when you see it, you know what it means. The following are equivalent. Okay, anyway, let's back to the proof. The proof is actually apply sequential characterization. Characterization of limit. Okay, you just apply the sequential of characterization of limit. You will prove it. It's not that difficult. It's actually obvious. Okay. So let's see then the other important theorem, which will guarantee the evaluation or the verification of a continuity for some complex functions like the addition, subtractions, scalar multiplication, and product and quotient. Okay, because of this sequential characterization of the limit, and because of the corresponding sum, difference, product, quotient, limit properties, we have the following theorem, which we will never prove because it's so trivial. So let E be a non-empty subset of R, and f g from E to R if f g are continuous at a point A in E. Here we also have respectively continuous on the set E. So you can discuss the situation when it is just when they are just continuous at a single point, or you can say the statement the theorem when two functions are continuous over the set E. The same thing. Then so on. So on means the following functions are also continuous for the corresponding situation. So the sum f plus g, f times g, and alpha times f for any alpha in R scalar multiplication. Okay. Moreover, okay, so those are always correct. And moreover means there's some additional stuff. Moreover, f over g is continuous at A. What one? There's some condition. 1g of A is not equal to 0. And if it is always continuous over the over this set, they say respectively on E, 1g of x is not equal to 0 for all x in E. So if you're talking about the domain, you have to make sure that this G is non-vanishing over the whole domain. So that's what it means. G has to be non-vanishing over the whole domain. For example, if you have x squared plus 1, let's write this example here. You have x squared plus 1. This is f. You have x. This is g. They are both defined from R to R. That's good. And if x is not equal to 0, then f over g is continuous. Continuous. A, no, let's not use x. That's A. If A is not equal to 0, f over g is continuous at A. Okay, obvious. But f over g is not well defined on the whole set R, because on the at 0, because g of 0 is 0, so it's not always non-zero. But if you flip it, then g over f is continuous over the whole real line R, because f is never equal to 0. So when you talk about a single point, it's okay. Single point you can just require at that single point function is not 0. But if you define the quotient over the domain, whole domain, you have to make sure that denominator is never 0 over the whole domain, right? Let me see. And next, right after this theorem, the author mentioned some, hold on a second. Mentioned some other construction. Let's see what constructions we have. This construction, see, on page 65. On page 65, there are several other constructions. Let me list them. Okay, so we have fg continuous at A in E. Then we have Ops value function. Ops value function we know it is. And f plus. What is f plus? F plus means you have Ops value function sum with fx and divided by 2. This is f plus. It's a positive part. Actually, it means the max between fx and 0. Max fx and 0. Okay, so f plus and f minus. This is some useful construction. You may not always use it, but sometimes you use it. F minus. F minus is negative part, but we want the negative part positive. Okay, so it's a opposite value minus fx. If it's positive, fx positive, the difference is 0. If fx is negative, you actually get the negative of the positive part. So actually, it's like this. Okay. Okay, f plus, f minus, and one of the important property is that fx is positive part minus negative part. So every function can be a difference of two positive functions. They're both positive, non-negative. Every function can be a difference of two non-negative functions, always. And opposite value of fx, f plus plus f minus. Okay, so if g continues, then f opposite value f plus and f minus are both continuous. From here you can see it's continuous. Okay, so this is a one construction. The other construction, f g. This one means here you see, you do not just select 0, you select g of x. The larger one, the maximum among them. Okay, and f wedge g, so it's a minimum among them. Okay, and then this one, it has some formula in terms of algebra. Okay, this is exactly what the exercise wants you to prove on page 65. We didn't do that part, but if you're interested, you can do it. It's not difficult. It's just understanding of a plus or minus, greater and smaller. Okay, so this is this function. These two functions are also continuous if f and g are both continuous. You can see that actually, if you have, this is f, this is g, then what is this f wedge g? F, the first one, it's actually this part. This top part is f g, and this one is the bottom part. We always choose the minimum. Okay, of course they are continuous functions. The graphs are connected, right? They're continuous functions. All right. So anyway, this is just an exercise. If you want, you can practice. It's not required in the exam. I don't want to give you more parts because they are important, but they are not on the main lines. They're useful. They are useful tricks. And of course, we will see that all the polynomial functions are continuous. All the polynomial functions are continuous. Let me write it here. Over R. Okay. The next is composite function. The composite function. What is a composite function? the composite function is very important, and also we have the so-called the chain rule. Chain rule is related to the composite function, right? So to study composite function, actually we have to compare it with the addition, subtraction, multiplication, division part. But anyway, first let's do the definition. Suppose that A and B are subsets of R. Of course, here we always mean non-empty subsets, and that F from A to R and G from B to R. Okay, if F of A, the image of A under F, is contained in B, then the composition of G with F, the composition of G with F is the function G circle F from A to R defined by G circle F of X is equal to G of F of X for X in A. Okay, so that's the composite function. So here, let me, I believe all of you understand the difference between the composite function and the addition subtraction, but still I need to write it down. So if you have F and G both from A to R, they're from the same they are defined over the same domain, and they both map to R. Then you have F plus G. They share the same input. But G compose F is actually the following like this. So you first have A, and then you apply F, you get a B, and then you apply G, you get R. So it's a step-by-step operation. Okay, and F and G have different input. Okay. All right. That's the difference between the composite function and the regular addition subtraction stuff. Now let's see the continuity of the composite function. The continuity of the composite function is the following. Suppose that A and B are subsets of R. And that F from A to R, G from B to R. With FA inside B. Okay, then if A is the interval I, but without the point A, where I is a degenerate, non-degenerate interval. Degenerate interval will mean a point. Non-degenerate interval, not point. That either either contains A or has A as one of its endpoints. Points. If L is the limit fx, x approaches A, x inside I, okay, exists. If this limit exists and belongs to B, and if, so it's a long stuff, and if G is continuous, at L belong to B, then what we have, actually we have, let me write this one. We have the limit x approaches A, x inside A, I, g of f of x is equal to g of the limit x approaches A, x belong to I, f of x. Okay, so this, in the first part of the theorem, we are not done, but in the first part of the theorem, we only assume the continuity of the exterior function. So we have interior, exterior. F is interior function, G is exterior function. We only assume the continuity of the exterior function. And then the limit will exchange between the exterior function and the limit operation, right? So that's what it means. We don't assume the continuity of f, because you see here, this A is actually may not contain A, the point A. The interval A may not interval A. The domain A may not contain A. We exclude A. We don't care if it contains or not, technically. That's about the limit evaluation. Okay, and second part is about continuity. First part is actually the limit of the composition of f and g. And second part is the continuity of the composition f and g. So if f is continuous at A, in A, and the g is continuous at Fa in B, then G circle F is continuous at A. All right, so it's a the continuity of the composition of a G with F. Okay, so again, this one, it's easier if we can apply the sequential characterization. Let me give the proof. Or let me copy the proof. The proof is not difficult. So let xn belong to I without A. We were proving part A, part 1. We choose a sequence, and xn approaches A as n approaches infinity. So fa inside B, fx, or it implies fx belongs to B. And sequential characterization, L x approaches A, x in I, fx, this limit implies xn approach, not xn, fxn approaches L as n approaches infinity. It's a sequential characterization of a limit. Sequential characterization of limits. Okay, then what it means? It means G is continuous. Remember, there is a characterization right after the definition. G is continuous at L. G is continuous at L. Then fxn, this is considered as a sequence, converges to L as n converges to infinity. This condition implies G of fxn converges to G of L as n converges to approaches infinity. G is continuous, then you definitely have this. And this is exactly what you need. You're done. Because for every sequence fx with this, then you will have every xn converges to A. You always have a G of f of xn converges to G of L, then the limit is always this. Again, by the sequential characterization of limit. Okay, so you see here, for all xn converges to A as n approaches infinity, we have the G f xn converges to G of L. Then the sequential characterization. Here, remember, this implies the limit of the limits. Implies x approaches A, x in I, G of f of x. This limit is equal to G of L. G of L. G of L is the limit x approaches A, x belongs to I, fx. So that's exactly the part of 1. Okay, so you use sequential characterization for the limits twice. So one time you go from limit to the sequence. The other time you go from sequence to the limit. Okay. Okay, so okay, that's it. This is part 1. Part 2 is just a corollary of part 1. There's nothing you need to show. So part 2 is a corollary. 2 is a corollary of 1. 2 is a corollary of 1. Okay, so that's the continuity of the composition of G with F. And you see here for the continuous function, if we sketch the graph, this is continuous. Or you do this is also continuous. Whatever you just sketch a connected graph is going to be represent a continuous function. But for this function, the second wave function I draw is so-called bounded. It's covered by a horizontal strip. But if we have the parabola, it's unbounded. It can never be covered by the horizontal strip. If it can be covered by the horizontal strip, we call it the function to be bounded. So let E be a non-empty subset of R. A function f from E to R is said to be bounded on E. If and only if there is a number m in R, of course positive normally, such that ops value fx is less than or equal to m for all x in E. So from this condition, we know it is positive. Okay, so this is m, this is negative m. So that's how we get this horizontal band. Horizontal band. Not every function, not every even continuous, not every continuous function is bounded. For example, parabola is not bounded. But if we restrict the parabola to an arbitrary closed interval, if we restrict it to arbitrary closed interval, you will see that it's limited to, because you have the ends, you cannot approach infinity. You have ends, so it will be bounded. So this is not a special property of a parabola. It's a property for the continuous function over the closed interval. Again, it must be a closed interval. This is not a theorem. This is a definition. This is a definition. This is a definition. You see, if it's not a closed interval, remember I think this is cotangent, graph of cotangent. Yeah. The graph cotangent looks like this. It's from 0 to pi. The domain is from 0 to pi. It will approach positive infinity, negative infinity at 0 and at pi. And this is unbounded. The domain is an open interval. So it has to be a closed interval. It has to be continuous function. So that's our famous extreme value theorem. The extreme value theorem. I'm going to prove the state and prove the extreme value theorem in the next video. So far we stop at this moment. Okay? Thank you. I will do the theorem 3.26 in the next video. Thank you very much.